The next part of this unit is on rate laws. There are two types of rate laws that we're going to learn about. The first is called the differential rate law. And the differential rate law expresses or reveals a relationship between the concentration of the reactants and the rate of the reaction. We usually simply call the differential rate law just the rate law. So if you hear just the word rate law where it says calculate, determine the rate law, they're talking about the differential rate law. The differential rate law is usually just called the rate law, as I just said. The second type of rate law that we will not look at in this video, but a future one, is called the integrated rate law. It expresses or reveals a relationship between the concentration of the reactants and time. So again, concentration of the reactants, but in the differential rate law, it's the relationship between the concentration of the reaction and the rate of the reaction. Whereas the integrated rate law is relating the concentration of the reactants to simply time passing by. The differential rate law and the integrated rate law are related for a given reaction. Now, when writing a differential rate law, we will consider the conditions where the reverse reaction can be completely neglected, so that the rate of the reaction only depends on the reactant concentrations. Again, we're going to be considering the time of the reaction where only the reactant concentrations are important, and these are the initial concentrations. This is immediately after the reactants have been mixed. So just in your mind, think about before the reactants have touched or come into contact and the molecules have collided. No products have been formed. That's the point in the reaction that we are considering. Immediately as you mix the reactants and they initially start to react, that is the point in time that we are studying in this type of calculation. So for the reaction, NO2, two NO2s yields two NOs plus O2 that we were looking at in the first video. You would write the form of the rate law. This is called the form of the rate law. Okay, it's not complete until we actually solve for the exponent here, which is referred to as the order. But the form of the rate law does not take into consideration either of the products, so you're only looking at the reactant. So you would write rate equals K. K is the rate constant, and it's constant at a given temperature for a given reaction, times the concentration of NO2 raised to the nth power. Now we actually are going to solve for these exponents in the next video. The exponent here is referred to as the order of the reaction. This number does not come from the balanced equation. We have to calculate it using method of initial rates. Now I want you to notice that the concentration of the products do not appear in the rate law, and that's because the reverse reaction does not contribute to the overall rate. Also, the value for N must be determined experimentally. So from experimental data, we will determine N. How does the rate law help us? Well, we can actually work backwards from our rate laws and infer the steps by which the reaction occurs. And those steps are what we mentioned in the very first video, the introduction of this unit. They're called the reaction mechanism. We will talk about that later in this unit. To determine the form of the rate law, we use the method called method of initial rates. And this is as close to time equal to 0 as possible. So immediately after the reactants have been mixed. So how does it work? Well, what happens is we have several experiments that are carried out using different initial concentrations. And then initial rates are determined. Once that has occurred, the results are compared to see how the initial rates compared to the initial concentrations. Now, in the next video, I'm going to take you through this example. The first thing you've got to do, though, is to determine the form of the rate law. Now, the reaction that is involved here is not the same one we've been looking at. The reaction here is NO plus Cl2 yields NoCl, and so the coefficient will need to be a 2, 1, 2. So this will be the reaction that we're using. And you'll notice 4 experiments have been carried out. And there's the 2 reactants here are nitrogen monoxide and chlorine. So that's why you see concentration of the NO has been measured in each experiment, and the concentration of chlorine. And the initial rates, this is the initial rate. Again, method of initial rates is what we're using. Now, the first thing you got to do is to write the form of the rate law. And that means your exponents, your orders are going to be, for now, letters that we have to solve for. Now, some books use N, M, and O, but the O looks like a 0 order to me, so I like to use X, Y, Z on my examples. So before the next video, let me just point out to you that the form of this rate law is rate equals K, because there's your rate constant, times the concentration of NO, our first reactant, raised to the X power, we're going to solve for X, times the concentration of Cl2, because that's your other reactant, raised to the Y power. We're going to actually solve for these orders in the next video, and then we'll have the actual rate law. Now, the overall order of the reaction for this one is obtained by adding your exponents. Remember, if you're multiplying numbers here, if you add your exponents to get the overall order, if you think about your exponent rules. So the overall order is X plus Y. But you could be asked about the order with respect to the NO, and that would be equal to whatever X is when we solve for X. You could also be asked about the order with respect to the chlorine, which would be whatever Y is equal to. In our next video, we will go through this example on how to solve for X and Y.